This video will look at bounding volumes. For ray tracing, we intersect the ray equation against the equation for every object in the scene. This dragon model has 1.25 million triangles. For an image of 1000 by 1000 pixels, there would be 1 million rays leading to 1.25 trillion costly ray triangle intersection tests if no bounding volumes were employed. The concept behind bounding volumes is that we surround objects in the scene by bounding volumes. If the ray does not intersect the bounding volume, then it cannot intersect any of the objects covered by the bounding volume. Therefore, we can safely set the pixel color to the background color. This image demonstrates a few key concepts. First, the box surrounds all of the triangles in the scene. Therefore, it is a bounding volume for the entire object. Secondly, we create this axis-aligned bounding volume to be as tight as fit as possible for this object. We can do this by finding the lowest and highest x, y, z in the scene and making this the two extreme coordinates of the bounding box. Thirdly, it demonstrates rays falling into three categories. The first category, as shown by the red highlighting here, is that rays that miss the object. For these, they only need to be tested for intersection against the bounding volume, and then we know that they cannot hit any of the object itself. The remaining rays hit the box and thus must be tested against the object. Of those remaining rays, some will miss the object, such as the ones in red highlight here, and for those rays we have tested against all 1.25 million triangles at quite some cost. We would like to avoid this cost by minimizing any voids between the object and the bounding volume. We should aim to use bounding volumes that have a low cost of intersection. So for example, bounding boxes, as in this example, bounding spheres, bounding cylinders, they all have relatively low cost intersection algorithms. We will now look at the impact on time with an example. First, we'll assume that there are 1000 by 1000 pixels in our image. Therefore, we will have around 5% of our rays missing the bounding volume in this example, and 95% of rays will hit the volume and therefore must be tested against the 1.25 million triangles in the mesh. So we'll have 50,000 rays will only need one axis-aligned bounding box test against the bounding volume, and since they missed, they need no further tests. 950,000 rays will need that one test, and since they hit the bounding volume, they could hit a triangle inside, and therefore they must be tested against the 1.25 million triangles inside the model. So we've only improved the speed slightly. So overall, around 4 to 5% of the computation time will have been removed by this. We will now look at bounding volume hierarchies. So first of all, we just had one axis-aligned bounding box around our model. Now we are going to split this into two. So the overall scene will have one box surrounding the dragon, but this will then be split into a left and a right. The left-hand side will only contain the triangles that are covered by that bounding volume. So let's say there's approximately 625,000 triangles on the left and also on the right-hand side. So now when we come to ray trace, we will trace the ray against the top node in the bounding volume hierarchy. And only if we hit it, we will then test the left and the right nodes. And then we will go on to test against the appropriate triangles. So here is the overall algorithm. For each ray, we first of all test it against the root. Either the ray will miss that root bounding volume, and we stop, give it a background color, or it will hit the bounding volume. Now we test it against the blue nodes, the left or the right. Has it hit either the left or the right node? If it hits the left node, we then test against the left-hand side of the model, the 625,000 triangles there, and if it hits the right, we test against those 625,000 triangles. So if we compare to previously, and we use the same assumptions, this time round, 5% of the rays will miss the bounding volume and no longer need any further tests. 95% will hit the volume and must be tested against the two bounding volumes this time. Of those, half of the rays will hit the left-hand side and must be tested against the 625,000 triangles, and the other half of the rays will hit the right-hand side. So we can now see that 50,000 rays need to have one test only, and those that hit the root node will be tested against the left and the right-hand side, and then the triangles as appropriate. So 950,000 rays will need 3 axis-aligned bounding box tests against the root, the left and the right, and also 625,000 tests against the triangles. In this case, we've improved the speed significantly, around 50% speed up over just against the triangles themselves. And we can continue making the bounding volume hierarchy deeper. In this case, we're using a KD tree, which has a split in 1 dimension at each level of the tree. And also I'm using the surface area heuristic algorithm, which is, rather than taking the center of the model or the center of the space, it's trying to select a plane that's going to maximize some formula. We're also simplifying things a little bit, which we'll discuss slightly later on.